What I'll be talking about, so I came at remote sensing from a physics and sort of a data statistical process point of view, and then some work in finance and statistical modeling in finance, and then remote sensing and the small satellite platforms. So I'm going to talk about what we're calling InsightGIS, and it's really about focusing on the analyst or the person that's interacting with the data that is derived from satellite imagery or whatever sources that we're talking about. We're saying analysts because we're really thinking so much of this room is about remote sensing and government and intelligence, where it's really analysts looking at pictures, looking at derived data sets, building footprints, and making conclusions. But I think that Will's talk from SparkGeo was fantastic. Could be about Frank. So maybe Frank's not doing taxation, maybe Frank's doing real estate valuation, and they want to know within a city block what the buildings are and how many floors each building has. Some of these you can derive from satellite imagery. Some of them you can't. And it's a very statistical use case, which means that small improvements in the data have a direct impact in the value to the enterprise purchaser, which is a quality of not just satellite data, but derived data, machine learning, remote sensing, that I think is really important for solving this problem of selling to enterprise. So when I go through this talk and I say analysts, think about whoever the user of the data is, and the problem that we're solving is that real interaction of a user with some data, and then the developing of best practices to really close that loop, and its ramifications on a lot of the topics that we're talking about when we're talking about data derived and machine learning. So this is my favorite graph. This is what got me interested in small satellites in the first place. So this is the number of downloads for Landsat tiles starting in 2008 and going forward since the release of the archive. The reason why the number of downloads have exploded over the last 10 years is because it gave analysts a selection of temporal time series of data to look at. It's why STAC is such an important concept, or one of the reasons why STAC is such an important concept, why time series are such an important concept. I think the thing that's really important about this to me, though, is that not only the number of downloads, but the number of peer-reviewed papers, number of applications, number of people who know how to use Landsat data, and the amount of code that's been written to produce those algorithms have all exploded. All this isn't out there. It's on Google search. It's on many of the people in this room's laptops. Got to get that to people who will be paying for it, really operationalizing. That's the point. We know that AI is going to be changing all of this further, as well as data fusion and cross data. We know that in the next 10 years, that's going to be creating a very large impact. The current market for value-added reselling of data is about $7 billion. It's going to double over the next 8 years. There's a lot of money to be made by people who know how to take satellite data, turn it into things for Frank or anybody else. So what we're doing at Starlight is our first product has been our multiple MVP product has been a remote sensing development kit. So this is an infrastructure, Python SDK, and cloud tools to be able to bring data to a Python development environment, deploy machine learning, and really it's intended to be given to remote sensing experts who don't know anything about development ops, who haven't found Sentinel Hub or Google Earth engines entirely fitting for their needs yet, are looking to make development into commercial spaces to really access that market. So we want to be a facilitator for that. And the reason for that is that we want to form a platform that brings together all of these different kinds of applications into one place. Because when we go to enterprise customers, what you need is this concept of the whole product. It's not just enough to take a temporal stack of data and produce a crop type forecast. You need to do crop type, you need to do yield forecast, you need to do drought monitoring, you need to do insurance for black blight. It's really about this synergization, which is what allows you to go into an enterprise environment and start selling these things and finding a pathway there. And so we're doing that by facilitating the people who have the know-how and bring it together. So like I said, and has been mentioned a few times here, we're really interested in solving the problem of the person who is looking at the derived data, and that smartphone, that clipboard if it's Frank, his cell phone, is interacting with whatever cloud applications we've built, maybe updating in real time. As not only does Frank have a prioritized list of where to go visit these buildings, but as he starts looking at some of them, maybe it updates the model a little bit and redirects him. Maybe it's a tactical fire fuel map, right? You start making certain models, you reduce certain biases in your algorithms in a very statistical sense that actually adds on additional layers of efficiencies and costs. And then the purpose-chosen satellite sensors, this is matching the right sensor to the right user, to the right application rather. And these are really where the field's going. So we're here for STAC and ARD. And Landsat has taught us that there's lots of algorithms out there that can turn pixels into some kind of useful maps. And we're all searching for that way of turning useful maps into some kind of actionability for a person on the ground. One of the reasons, I forgot to mention this at the beginning, but when you talk to enterprise customers, they don't necessarily need satellite. If there's a business process or a data process that is valuable to them, they already have people doing it. So where there are people, they're doing processes that are creating the value, and it's really about optimizing their life, just to reiterate the same point. So as we bring all these different data sets together, which is the kind of standardization that ARD, STAC and ARD will do, that's really a protocol for interoperability across different data sets. In order to get that to a frontline consumer or a frontline specialist who's able to build that last mile product, we need to, when a novice user comes to this sort of great big ecosystem of data that we have, understand their intent, be able to predict what it is that they're going to need, provide those predictive needs, and then really create the feedback loop that as users are interacting with our products, we're able to identify better ways that they could be using products, better derived maps that could be generated to help the next generation of product or the next satellite sensors that are required. So as I said, we're focusing very much on this SDK for building these algorithms that are Python code that pull together really any kind of data and produce interactive algorithms for analysts to work with. And then we're capturing that interactive data interaction. We have a project that's really intended to focus directly on STAC specifically, which is to be able to, we want to start taking these Landsat applications and building them in this abstract language called Ether that we have that are for Landsat, but then be able to automatically port them over to different kinds of data sets. Okay? And because we have this protocol for analysts interacting with it, as errors are found, if you take a cloud mask from Landsat and put it onto a cloud mask for Sentinel, you have someone there that's already gathering the feedback of where that model's working, where that model's not working, and it's shifting towards this sort of ecosystem of interactivity with the data. And we are building currently a software architecture that is intended to be a kind of hub in which people bring together multiple different kinds of data, that bring together multiple different kinds of applications on that data and collecting the interaction in real time. I think I'll pass over this just for the sake of time, but if anybody's interested in analyst work, value-added reseller work, and interactivity with data, by all means, please come talk to me. If you're interested, definitely we want to help you solve ground truth problems, ground truth and data labeling problems. I'm going to go through a handful of slides here to hopefully make a case of why machine learning all the problems that exist today in machine learning will never go away. And so what we need to do in this room is to come up with best practices for the holistic approach of trying to take data and generate some kind of new data from it. This is the SpaceNet 2007 July Building Footprints Challenge. So the best model, I don't know what it's been updated right now, but the best model then was about 80% accurate. So you take like the best deep learning in the world, the best training data in the world, the best satellite imagery for it, and you get 80% of buildings. But how many of those solutions need 100%? So what you're really doing is you're figuring out ways to use machine learning so that the analysts, as someone from SpaceNet spoke yesterday, sure, it still takes a couple of hours to take whatever partial map has been produced and clean it up, but it would have taken weeks without the machine learning. It's that kind of feedback loop. And in fact, the competition winner from earlier in 2017 had a very large human component. So this really gets to sort of I hope, what communicates some value to all of you in the practices of machine learning from my particular perspective over the years, is that whether or not you're collecting crowdsourcing data, let's say Mechanical Turk, or you're having people out in the field taking images, or you're Frank, or your training data exists itself. There's great training data within it, or great crowdsourcers, or great analysts within there. There's really bad ones. And the truth is that the bad ones are so much more costly, we never even think about that. And I'll try to set that up in the next couple of slides. But what our InsightGIS platform is it's a platform for analysts to interact with the data, and in the background there's machine learning automating their activity and trying to emulate the analysts themselves. What this allows it to do is to record things like behavioral signatures that are able to identify a particular building footprint as drawn by an analyst may be more or less accurate. Okay? It allows the machine learning models that are deployed to find things like building footprints to then actually be watching the work of the analyst in real time and check that, that building footprint's actually probably wrong. Or that one's the great one, or like this analyst is a rock star, that one's not, right? And to do this in a very automated sense, in a way that just kind of requires fewer scientists building fewer models and more of this stuff automated across more kinds of applications that a person might be, an organization might be using. This is from a case study that we've run. So let's say we have a team of analysts making those building footprints. We all know the 80-20 rule. We all know that some of the training data is good, some is not. We call it the 540 rule. So a 5% increase in the accuracy of the analyst in creating your training data. So data labelers, Frank out in the field, the business, the farmer who's been told to go take a photo of some black spot on the crop that might be something they have to report to insurance or not. A 5% increase in their accuracy drops the overall holistic cost of being able to deliver consistent results by 40%. Okay? Simply by virtue of when you are paying someone to record bad data, they're actually biasing your models poorly. You need to have additional people to confirm that, and lots of other factors. I'd love to talk to you about this stuff, but it's really a subject of operations research right at that machine learning analyst nexus, and it's huge. It's huge. So these are some case studies that were done that I did in natural language processing. So this is categorizing text documents that really demonstrates sort of the powers of automation. You can start deploying very lightweight machine learning models, the kind of stuff that everyone in this room already knows, but in this like active learning human in the loop process that increases the overall accuracy of whatever data you're producing. So something as simple as land classification models drastically cuts down the time by factors of 10 or more, accuracy and ultimately the cost. I think I'm running out of time, so I'll speed along. This is a platform for interacting with maps that is architected in a particular way, that is going to leverage STAC and ARD concepts to bring together data that is from multiple types of satellite imagery, multiple types of mode, and really focusing on the analyst producing the highest quality of the data and getting to things like granular trust and provenance. So I'll leave that up there. That's the end of my talk. Thank you. Yeah.
Thank you for the great talk. I think we have time for some questions before lunch, if there are any.
How many of you have used machine learning to produce some sort of classification map or objects? Awesome. at any point you were listening to my talk and wondered what the heck it was I was talking about, I hope that you'll come talk to me about it, or I'll try and find you afterwards or at lunch.
Do you see more value in applying this kind of technology to something that's utilitarian like OpenStreetMap?
Yeah.
Understanding operational biases, or maybe more for the intelligence community, which leverages that data, to sort of enrich their, sort of understanding of the world?
Yeah. Yeah, no, that's a great question. That's a great question. So this is geared towards the intelligence community just because of where we are in our product development, in which case they have problems of using OpenStreetMap data, but they don't trust it yet. We've had all these conversations yesterday about, God, we want to know who pre-processed something to pre-process something else so that we can trust the data. In which case something like this is very useful for creating that chain of command and recording all of the transitions of data, including the ones that are interacting with analysts. Who told me this was a building? But for OpenStreetMap, for commercializing OpenStreetMap, this or this is really what's the missing heat. Because there are completeness problems, there are varying accuracies across the data collectors, and this is about giving someone that's doing OpenStreetMap a tool as they're interacting with ID to say, actually our lightweight algorithms have said this probably isn't correct. We're going to automatically send that to another analyst to scale up the collection of that data. It's exactly the kind of use case.
I really like this graph. I like the 540 rule and the importance you're placing on having well-tagged and true data.
Yeah.
Do you have a sense, or do you guys build tools around just understanding how much truth data is enough?
Yeah.
In terms of sampling and what that truth is within a given area, or as well as spatially as well?
Yeah, that's great. We are looking for the right use cases to demonstrate that too. And we should talk if it's something that you're very specifically interested in. This slide, which I glossed over, is about the life cycle of how you sort of, you collect some training data, you deploy a partial automation model, and then you have people doing quality control. And that question of sort of when do you make that transition over to saying enough training data is here? How do you create those metrics and deliver them? And one of the nice things about this holistic framework is that because you never really expect to not have someone interacting with doing quality control or picking the exceptions to things that the algorithms couldn't do. The one place where the SpaceNet algorithm doesn't apply, the towns where it doesn't apply, you still have analysts doing that. That you're always calibrating your models and you're always calibrating your training data in a very statistical sense that tells you as a byproduct exactly whether or not you have enough data for all buildings to 98% accuracy. Yeah, it's exactly that kind of deliverable. Yeah. And so the short answer is we are looking for ways to take what we're building and create a set of API tools that it basically would allow the collection of training data in a more efficient way, or the measurement of a partial algorithm and say, this definitely needs more out. Where geographically does this need more data? Things like that. Yeah. Yeah.
Have you tried or considered algorithms that will tell you how confident they are in the output? Like knowing whether this building or this image is close to what the algorithm has seen and trained on, or whether it's distant from anything else that we've seen and should have an analyst look at.
Yeah. So for the most part, that's a byproduct of almost all machine learning. So, and sort of core to this whole process, right? And the best practices of it. So this is on the right is the 3-step process for the winning SpaceNet building detection algorithm. And what this person did was they took the training data that was produced by SpaceNet, they classified each pixel as being a boundary pixel, an inside pixel, an outside pixel, which is actually using random forests, which is actually like a really simple model. Used that to generate polygons, and then used the scores that were produced by the random forest model to basically prioritize the polygons as they were output and start with the worst ones first and say the ones where the model is most uncertain, that one was wrong, that one was wrong, that was wrong, that was wrong, that one's right, that one's right, that one's right. Which is the sort of interaction between improving your data and how confident the model is on a particular instance of something. And then you can imagine cases in which you take that separate training data and just build a separate model, plug them together, things like that. Does that answer your question?
Yeah, well, there's two different kinds of uncertainty in machine learning. One is when the model has enough training data, but it can decide between one class or another. And the other is where the model just doesn't have training data around that sort of input.
Yeah, so what do you do for cases in which the algorithm is now looking at something that it never saw in training data? And part of that goes back to if you reframe your whole problem saying there's always going to be analysts looking at something, there's always going to be someone there to say, first and foremost, the algorithm is going to perform poorly on something that wasn't in the training data. And so it's very likely that will get thrown to an analyst to then inspect it. And then you start delivering, you either start identifying new classes or new categories, or you start gathering training data for that particularly difficult exceptions. Yeah. Yeah.
I think it's probably best to continue offline.
Please come up and talk to me afterwards.
Lunchtime now.
Love to. Thanks.